So if we want to quantify the change in volume due to a change in temperature, we're going to go ahead and use this same format. However, what we're going to do is we're going to change the subscript from a 1 to a 2 to represent the final state. So in other words, V2 over T2 is equal to some constant. And so if we, and so this is going to represent the final state of the system. So if we put these two equations equal to each other, we're going to get V1 over T1 is equal to V2 over T2. And so this constant doesn't necessarily disappear. We're just saying that this constant is equal to this constant. So therefore, V1 and T1 is equal to V2 and T2. So this equation, V1 over T1 is equal to V2 over T2, is known as Charles' law. And we can go ahead and use Charles' law to quantify changes in volume because there was a change in temperature. Now, just a quick note, when you're using Charles' law, you guys must convert temperature into Kelvin units. And so, for instance, if you have 25.0 degrees Celsius, and if you want to convert that into Kelvin, you're just going to go ahead and add 273.15, giving us 298.15 Kelvin. The reason why we want to use the Kelvin as our unit of temperature is because the Kelvin units does not go into the negative values. And so if you think about Fahrenheit, the scale for Fahrenheit, the scale for degrees Celsius, the negative values of those temperature units can occur. And if you plug them in without changing them into Kelvin, what you're going to get is a negative answer for volume. And we know that volume cannot be negative. And so you just can't have missing volume, or you can't have negative volume. Volume will always be positive. And so to ensure that our calculations are always positive, we always want to convert into Kelvin units first before we plug things into the formula. In regards to the unit for volume, just make sure that they're the same. It doesn't matter if it's in milliliters or liters, but if, for instance, V1 is in milliliters, V2 must also be in milliliters. So you just want to make sure that both V1 and V2 have the same units, and T1 and T2 are in Kelvin units. Just kind of reviewing that same concept for Boyle's law, since temperature is not found in Boyle's law, we just want to make sure that the pressure units and the volume units are the same. So for example, if P1 is in atmospheres, then P2 must also be in atmospheres. However, if P1 is in Pascal units, P2 can also be in Pascal units. You don't necessarily need to change everything into atmospheres. Just make sure that the unit for pressure and volume are the same on both sides. Cool. So that pretty much sums up what we discussed in lecture 2 weeks ago. And so let's go ahead and start looking at our new relationship. So the relationship that we're going to discuss next is known as Guy-Lussac's law, and it basically creates a relationship between pressure and temperature. And so let's go ahead and move the screen down. So what would happen to the pressure of the gas if there's a change in temperature. Okay. So let's go ahead and think about this conceptually. Before we do that, we have to understand that there are no changes in volume or amount of gases. So long story short, volume and amount of gas or moles of gas is held constant. And we're only looking at how pressure is affected by changes in temperature. And so if we think about, if we look at a specific example, we can understand the relationship between the two. So let's just say that we have some type of container, and since volume is held constant, this is not going to be a balloon, nor is it going to be a movable piston. And so let's just say that the volume is constant. So we can just have like this box, and none of the walls of the box can move. So let's just say that we have these gas molecules that are inside this container, and the current temperature is 0 degrees Celsius. In Kelvin, that'll be 273.15. Now, if we increase the temperature of the system, so we're going to add heat. So once again, that triangle over the arrow sign is going to represent heat in chemistry. What we're doing is we're adding kinetic energy to the system. And so these gas molecules, when we add heat, is going to allow them to increase their kinetic energy. And if the volume of the container is fixed, what's going to happen is that these particles with an increased kinetic energy, it's going to collide with it's going to collide against the surface of the container a lot more frequently. And if you have more collision, so to speak, it's going to exert a greater force on the surface of the container, and therefore the pressure of the system or the pressure of the gas is going to increase. And so by adding kinetic energy in the form of an increase in temperature, it's going to increase the pressure of the gas. And so, once again, very similar to volume and temperature, there's a proportional relationship between pressure and temperature, such that if you increase temperature, you increase the pressure of the gas. And if you decrease temperature, the pressure of the gas will drop. So it's going to decrease the pressure of the gas. Okay. So once again, here we have a proportional relationship between temperature and pressure, such that mathematically we can go ahead and write T is equal to P times, once again, some constant. Okay. And so we're deriving all of these mathematical equations from the concept. And so since there's a proportional relationship between temperature and pressure, if we solve for the constant, we get T over P is equal to some constant. And so we can go ahead and take this fundamental mathematical equation, if you will, and we can go ahead and use this to represent both the initial state and the final state, such that for the initial state, we can say that T1 over P1 is equal to some constant. And for the final state, T2 over P2 is equal to the same constant. And so the changes between initial state and final state was once again caused by temperature. And so since these constants are pretty much the same, we can go ahead and make them equal to each other such that T1 is equal to P1 and T1 over P1 is equal to T2 over P2. Now, another way that you guys can see this form is basically it's opposite, it's reciprocal. And so, for example, you might see P1 over T1 is equal to P2 over T2. And these forms are equivalent to each other, so you wouldn't be wrong if you used one or the other. And so this mathematical relationship is known as Gay-Lussac's law. And so let's go ahead and talk about the units once again. Once again, since temperature is present in our equation, we must make sure that all temperature unit must be in Kelvin. So this is a must. It must be converted into Kelvin before you plug it into the equation. And so when we're looking at pressure, it's not really, there's not a specific pressure you must conform to before you plug your numbers into the equation. You just need to make sure that all pressure units are the same on both sides of the equation, or both sides of the equal sign. All right, cool. And so that's pretty much the relationship between pressure and temperature. And so scrolling to the top part of our page, here we've covered the relationship between temperature and pressure. So this is known as Gay-Lussac's law. And we went ahead and discussed the relationship between temperature and volume, and that was Charles's law. And the relationship between pressure and volume, or volume and pressure, is going to be Boyle's law. So the last thing that we need to discuss is the relationship between the amount of gas molecules and for example, volume or temperature or pressure. So let's go ahead and do that. So when you're comparing the number of moles of gas against volume, This relationship is referring to Avogadro's law. So interestingly, the number of this relationship that was observed by Avogadro enabled him to calculate Avogadro's number, which is 6.0221 times 10 to the 23rd power. And so, in regards to the concept of this topic, we're going to see how changes in a mole of gas affects the volume of the gas. And we can go ahead and understand this concept by once again looking at a balloon. So here, let's just say that this is the initial state. We have a specific amount of volume, and we have a specific amount of gases inside this balloon. And so if we wanted to, let's just say, blow up the balloon, so temperature is held constant and pressure is held constant in this case. When we blow a balloon, what we're doing is we're increasing the number of moles of gas. And so if you imagine blowing a balloon, you're going to increase the volume overall. And so when we add more moles of gases, or more gases just in general inside a container, in this case the container is a balloon, we're going to increase its volume. So that we're going to add moles of gas. And the final state will have an increased volume of the gas. Okay. And so if we take a step back and think about the relationship between moles of gases and volume of gas, if we add more moles of gas, then that means that we increase the volume of the gas. So overall, there's a proportional relationship between the two, such that volume is proportional to N. So N is going to represent moles of gas. Okay. And once again, we can go ahead and multiply this by some constant. This gas constant, which we will discuss later, it's just a constant. Its value just doesn't change. And so we can go ahead and use this mathematical relationship to be able to write or express the relationships between the initial state and the final state. And so to do so, we're just going to go ahead and solve for the constant. So V over N is equal to this constant. And so we can go ahead and use this fundamental equation, if you will, to represent both the initial state and the final state, such that V1 over N1 equal to some constant is going to represent the initial state, and V2 over N2, or the number of moles of gases, is going to equal to that same constant, and this is going to represent the final state. And so once again, since these constants are the same, we can go ahead and set them equal to each other. And if we set them equal to each other, that's going to give us an overall equation such that V1 over N1 is equal to V2 over N2. Okay. And once again, the 1s will represent the initial state and the 2s will represent the final state. And so if you had changed the number of moles of gases, how is that going to affect the volume of the system? And so that's going to be represented by V2. Cool. And so this relationship is known as Avogadro's law. It's a proportional relationship, but when you guys are using the equation, it's going to be V1 over N1 is equal to V2 over N2. So in terms of the units to keep track of, both volume and moles of gas must be the same. In other words, if V1 is in liters, V2 must also be in liters. If V1 is in milliliters, then V2 must also be in milliliters. Now, for the value for N, the unit for N must be in moles. And so if the problem, for instance, presented the unit as mass or grams, then you need to convert from grams to moles using the molar mass of the chemical formula to perform that conversion. So very similar to the idea of temperature always being expressed in Kelvin, when you guys are solving for N, or whenever you guys are using N to plug into this equation, it must be in units of moles. And for volume, just make sure that they both have the same unit. Cool. All right, so another relationship that Avogadro was able to make between volume and the number of moles is this idea of standard temperature and pressure. So standard temperature and pressure, or STP, allows us to go from moles to liters at a very specific temperature at a very specific pressure. So the standard temperature, so let me go ahead and write that down. So I'm going to go ahead and put in the standard temperature is going to equal to 0 degrees Celsius. Or 273.15 Kelvin. And standard pressure is equal to 1 atmosphere. And so basically what Avogadro did was he saw that there was a relationship between the number of moles and the volume at this specific temperature and at this specific pressure. And so if the temperature of the environment is 0 degrees Celsius and the pressure is 1.0 atmospheres, he basically said that 1 mole of any gas will occupy 22.4 liters at 0 degrees Celsius and at 1 atmosphere. And so if the problem, if you guys are given a problem that utilizes STP, you guys can go ahead and make this relationship 1 mole is equal to 22.4 liters. If in the problem, the temperature is not, the temperature and pressure is not at standard temperature, not at standard pressure, then you guys cannot use this relationship between moles and volume. Cool. So let's go ahead and take a look at another relationship. Let's see here. Insofar, we've been able to make a relationship between pressure, volume, and temperature, as well as the number of moles. And so for this specific topic, we're going to go ahead and exclude the number of moles for now. And so if we take a step back and we look at our 3 laws, 3 main laws that governs pressure, volume, and temperature, we know that pressure is inversely related to volume, and we know that volume is proportional to temperature, and pressure is also proportional to temperature. And so remember that each of these equations was multiplied by some constant, right? And so if you solve for the constant, we get pressure times volume. That's equal to some constant. If you divide, if you solve for the constant using this relationship, we get V over T. That's equal to some constant. And last but not least, if we have pressure and volume, and if we solve for the constant, it's going to be P over T. And that equals to some constant. And so what we can do is we can create a mathematical equation amongst these variables. And so if you look at the position, notice that both pressure and volume and pressure, they're all in the numerator. So if we combine all of these together, we just get P and V. Now if you look at the denominator in these two relationships are temperature. And so therefore, we can go ahead and put temperature in the denominator. And so all of this is going to equal to some constant. And so we can go ahead and use this combined gas law. To create, to be able to understand how changes in either volume or temperature will affect pressure, or how changes in, pressure and volume, or actually can't make that, pressure and temperature affects volume. And so very similar to all of the derivations that we've done thus far, we can go ahead and use this fundamental equation, if you will, to make relationships between the initial state and the final state. And so if we're talking about the initial state of a system, we can go ahead and say P1 times V1 over T1. And then here we can go ahead and put in P2 times V2 over T2. And so once again, this constant is the same in all scenarios. So therefore we can make them equal to each other. And that's going to give us P1 times V1 is equal, P1 times V1 over T1 is equal to P2 times V2 over T2. And so this mathematical equation is commonly known as the combined gas law. And once again, we can go ahead and use the combined gas law if we're given, for instance, pressure, volume, and temperature for the initial state. And we want to know how changes in either pressure or temperature will affect volume, or any number of combinations that can be thought of. Okay. Cool. And so notice that for this specific topic, we only looked at pressure, volume, and temperature. And so let's go ahead and look at pressure, volume, temperature, and the number of moles of gases, and see if there's a relationship amongst these four variables. And so once again, we can go ahead and just kind of copy and paste everything that we have over here. So notice that P times V equals to some constant, V over T is equal to some constant, and P over T is equal to some constant. So let's go ahead and write that down. So P times V is equal to some constant, V over T is equal to some constant, and what was the last one? Oh, P and T. P over T is equal to some constant. Now, if we take in consideration the relationship between, for instance, N and V, so this is Avogadro's law. Volume is proportional to the number of moles of gases times this by some constant. So if we solve for this constant once again, V over N is equal to some constant. So notice that in this scenario, the number of moles of any gas is in the denominator. So if we incorporate that into our ideal gas law, we get P times V over T times N. All of this is going to equal to our constant. And so, throughout this whole lecture, you guys have been hearing me say constant, constant, constant. And so what is this constant? And so it turns out that the gas constant is equal to 0.0821. Now the units for this gas constant is very, very specific. I always advise my students to make sure to write their units for any of these types of problems in chemistry, just because these units will absolutely help you. It'll help guide you solve the problem, to solve the problem. So we're going to go ahead and take a look at how these units will help us solve the problem when we go through some practice problems for gases. So for now, the gas constant is going to be 0.0821. The unit is going to be liters times atmospheres over moles and Kelvin. And so if we plug in this gas constant into this term, we get P times V over T times N, and that's going to equal to 0.0821. And so this was that constant that can be plugged into every single one of these mini equations that we've kind of gone through. So let me be consistent and write my units. So liters, atmospheres over mole and Kelvin. And so we can go ahead and multiply T, temperature, and N to the opposite side. And what we get is P times V is equal to 0.0821 liters times atmosphere over mole times Kelvin. And then this is going to be times N times T. And so this gas constant can be substituted by a specific variable known as R. And so if I remodify my equation, I can get P times V is equal to R times N times T. Now, the most common way that this equation will be presented is going to be P times V is equal to N times R times T. And so this equation is known as the ideal gas law. Okay. And so you guys are going to be using the ideal gas law to determine one of these variables, whether it be pressure, volume, moles, or temperature, if you're given at least 3 of these variables and one is missing. So for example, if in the problem it gave you a value for volume, it gave you a value for amount of gases, and it gave you the value for temperature, you guys can go ahead and convert all of those values into liters, atmospheres, moles, and Kelvin, and then plug them into the ideal gas law equation and solve for pressure, for instance. And so that's one way that you guys can use this ideal gas law in a problem type setting. And so just to summarize what we've kind of discussed, we've discussed a lot of chemical, or not chemical equations, we've discussed a lot of mathematical equations that we can use to determine the number of moles of gases, or pressure of gas, volume of gas, temperature, etc. And so just to kind of review, we have Boyle's law, and Boyle's law is P1 times V1 equals to P2 times V2. Next, we have Charles' law, which is going to be V1 over T1 is equal to V2 over T2. And so Boyle's law, P1 times V1 equals to P2 times V2, it allows us to determine how pressure or volume is going to be affected by a change in either pressure or a change in volume. Charles' law allows us to determine, changes in volume based on changes in temperature. Gay-Lussac's law allows us to understand how changes in temperature affects the pressure. Avogadro's law allows us to understand how changes in volume, oops, is going to affect, how changes in the number of moles of gases affects volume. Okay. All right, and so another equation that we discussed is the combined gas law. And so the combined gas law takes into consideration pressure, volume, and temperature, and how changes in one or two of those variables will affect the other. So here we have P1 times V1 over T1 is equal to P2 times V2 over T2. And so if we take in consideration the number of moles of gases, we get our ideal gas law. Oops, can't spell gas. And so our ideal gas law is pressure times volume is equal to the number of moles of gas times this by the ideal gas constant times that by temperature. One thing that I want to mention about the ideal gas law when you guys are using this is the units. And so please remember that the units for the ideal gas law is in liters, atmospheres, moles, and Kelvin. And so since the units for the gas constant is very, very specific, what you want to do is you want to make sure that every single one of these variables are in liters for pressure, liters for volume, atmospheres for pressure, moles for amount of gases, and Kelvin for temperature. And so you guys need to convert every single one of the given values into these units, liters, atmospheres, moles, and Kelvin, to ensure that they're going to be canceled out as you perform the math. So for the combined gas law, very similar to Boyle's law, we want to make sure that pressure, volume is going to be the same unit on both sides. And you want to convert it before. Last but not least, since the combined gas law involves temperature, if you guys recall from earlier on, temperature must be in Kelvin units for gases. If your temperature is in degrees Celsius or degrees Fahrenheit, you guys are definitely going to get the wrong answer. If you guys recall, degrees Celsius and degrees Fahrenheit can go into the negatives. And so if, for instance, you have like negative 15 degrees Celsius and you increase the temperature to 25 degrees Celsius, if you plug in negative 15 into T1, there's no other negatives inside your equation that's going to cancel out that negative. And so your overall answer is going to be negative, and that cannot hold true for pressure and volume. So pressure and volume must always stay positive. Cool. Let's see here. So long story short, these are the main equations that you guys are going to be using to determine the amount of pressure and volume or temperature or moles that's resulted from a change in the other variables. Let's see. So for the ideal gas law, I do want you to note that how the ideal gas law is written, it's written as P times V is equal to N times R times T. So notice that there's no subscript. It's not like P1, V1 is equal to N1, R1, T1. And so because the ideal gas law doesn't have a subscript of 1 or 2, you guys can only use the ideal gas law if there are no changes in pressure, changes in volume, changes in number of moles of gas or temperature. And so typically, you guys will we'll do some practice problems in another video, but typically you guys will only use the ideal gas law if you're presented one value for volume, one value for pressure, one value for moles, and one value for temperature. Now, if you guys are presented two values for pressure, two values for volume, two values for temperature, and one of those values is going to be the item that you're solving for, then you're probably going to be using the combined gas law. Now, if you're given just two values of volume and two values of number of moles or amount of gases, then you're probably going to be using Avogadro's law. If you guys are given two values for pressure and two values for temperature, then you guys are going to be using Guy-Lussac's law. And if you guys have two values of volume and two values of temperature, you're going to be using Charles's law. And last but not least, if you have two values of pressure and two values of volume, you guys are going to be using Boyle's law. And so when we work through these problems, I'll go ahead and highlight this just so everyone's clear on what equation to kind of use. But overall, you always want to remember that if you're only given one value of pressure, one value of volume, one value of number of moles of gases, and one value of temperature, then you guys are going to be using the ideal gas law. All right, please move on to the next video, and we'll go ahead and learn how to use these equations to solve problems.